Hello, this is Bertsekas. Let me welcome you to a series of video lectures about my research in semicontractive dynamic programming. This is an important topic within the field of abstract dynamic programming, a somewhat theoretical subject that aims to unify the analysis of dynamic programming problems by focusing on fundamental theoretical properties of their dynamic programming mapping, the mapping that defines Bellmans equation. To provide some context, generally in infinite horizon dynamic programming, there is a division between easy problems and difficult problems. Easy problems are discounted problems, particularly with a finite number of states and controls, where the results that you ideally expect and hope to hold, in fact do hold. The key fact about these problems is that the mapping associated with the DP algorithm is a contraction mapping, and this enables powerful theoretical and computational results. For this reason, discounted problems of this type are often called contractive. At the other extreme, the difficult problems are the ones for which the DP mapping is not a contraction of any kind, and which we call non-contractive. There, some results that you would like to hold indeed hold, but there are exceptions, and sometimes very peculiar and unexpected behavior arises, and one should be aware of that. Moreover, in addition to understanding the peculiar behaviors, it is important to understand what kind of structure one should introduce into the models so that good results hold, results that are comparable to the ones for the contractive models. Now, semi-contractive models are intermediate between contractive and non-contractive. They involve the kind of structure that induces results nearly comparable to the ones for contractive models. At the same time, they exhibit interesting and peculiar behaviors that one should understand in order to apply these models in practice. In this series of lectures, we will focus on semi-contractive models, and we will do this step by step. First, through examples, mostly from optimal control and stochastic shortest path problems, as in this first lecture. We will then develop a general theory for the classical type of stochastic optimal control. Finally, through the methods of abstract dynamic programming, we will generalize to other models such as minimax control, sequential games, and risk-sensitive exponential type cost problems. Let us start by describing a total cost stochastic optimal control problem, which involves a discrete time dynamic system. Xk here denotes the state of the system at time k. It takes values in some space x. Uk denotes the control at time k, Wk denotes a random disturbance at time k, and the next state of the system is generated using the system function f from the current state, the current control, and the current disturbance. The control at time k is taken from some control space u. The disturbance is taken from some space w, which for mathematical reasons we assume that it's countable. And it has a probability distribution that depends on the current state and the current control. We're interested in policies, which are sequences of controls functions. Each function in this sequence, mu k, maps the current state xk to a control uk, which must satisfy a certain constraint, is chosen from this constraint set that depends on the current state. Now, given a policy and an initial state, we have a cost for each stage, and the sum of the costs over n stages is given by this expression. Here's the sum of the cost of the stages, but discounted with a discount factor that may be strictly less than 1 or may be equal to 1 in the undiscounted case. Now, this sum over the n stages is a random variable because wk is a random variable, and to make it a real number, we take its expected value. So this expression here is the expected cost over n stages, and we're interested in the total cost over an infinite horizon. We are not sure that this limit as n goes to infinity exists, so we take lim sup here to define properly j pi of x0. The optimal cost starting at x0 is the infimum over all policies of j pi of x0, and we're interested in an optimal policy pi star that satisfies this equation uniformly for all x. In this problem, a special role is played by stationary policies. Stationary policies are the ones where mu k does not change from one stage to the next. There's a single control function mu that defines the policy. Typically, there are optimal policies that are stationary, and for this reason, the stationary policies deserve special attention. And the adequacy of stationary policies is intuitively clear because of the fact that here we're dealing with an infinite horizon. So at time 0, the problem that we are seeing is the same as the one that we're seeing at time 1 from the same state x. So there is no reason to have a control that's different at time 0 than the one at time 1 if starting at the same state. Let us now introduce Bellmans equation for a given stationary policy. It has this form here, and what it says is that the cost of using policy mu starting from x is the sum of the expected value of the first stage cost plus the cost from the remaining stages starting from the next state and appropriately discounted. It captures the essence of the dynamic programming concept. Just as there is a Bellman equation for every stationary policy, there is also a Bellman's equation for the entire problem, where the optimal cost starting from state x typically satisfies this equation here. It's really the same as this one, except that we minimize over all policies. This is called Bellman's equation for the optimal cost. Now notice that there's one Bellman equation for every state, and this equation can be viewed as an equation to solve for the function j star or j mu. So these are functional equations in j mu or j star. And it's possible to take a more abstract point of view of looking at this equation, for example, as one transformation that is applied to the function j mu to produce the function t mus of j mu. In other words, this transformation here on j mu is denoted abstractly by t mu, and what Bellman's equation says is that j mu is a fixed point of this mapping t mu. Similarly, the Bellman equation for the entire problem can be viewed as a fixed point equation that can be solved for j star, where t expresses this transformation which takes a function j star into the function tj star. This abstract point of view is going to be significant as we progress in this lecture series. Now, from an analytical point of view, it is important when Bellman's equation has a unique solution. This is something that is usually true, and in particular it is true if all the mappings T mu are contraction mappings, because then T mu has a unique fixed point, which has to be this J mu. And if this is true, the problem is called contractive. Otherwise, it's called non-contractive. Contractive problems are much nicer than non-contractive problems. Let us discuss the difference between these two types of problems. Okay, let us now consider various types of stochastic optimal control problems. On one hand, we have contractive problems, the most representative type of which is when there's a discount factor, alpha, that's strictly less than 1, and the cost per stage is uniformly bounded above and below with respect to state and control. These problems date to the early days of dynamic programming. They were investigated by Bellman and also by Shapley in the context of sequential games. An important subclass of such problems is when the number of states is finite, the number of controls per state is also finite, in which case we naturally have a bounded cost per stage. This is the class of problems for which the nicest results hold. And the reason for this is that there's an underlying contraction property of the mapping in Bellmans equation, which accounts for the nice analytical results and also nice computational results for these problems. At the other end, we have non-contractive problems. The most representative problems of this type are shortest path problems. Here we have a graph of n nodes connected with arcs, and each node is identified with a state. There is also a special state called the destination that we are trying to reach from every other node. At each state, our control affects the choice of the successor state and also results in a certain cost. Now, there are deterministic and stochastic versions of the shortest path problem. The difference is that in deterministic problems, our choice of control leads to a unique next state with certainty, while in stochastic problems, the next state is determined according to a probability distribution that depends on the choice of control. Stochastic shortest path problems are also known as first passage problems or transient programming problems. They arise very often in applications. For example, in transportation problems of finding an optimal route through a geographical network, or problems of routing in communication networks. They arise in robotics, where we want to move a certain system from one starting position to another final position, subject perhaps to uncertainty in the laws of motion. Problems where we plan to reach a goal in the face of uncertainty. Finance problems in options trading and execution, where you want to choose on every day whether between exercising the option and terminating, or waiting for a better price in the future, which may be subject to uncertainty. There are also problems of optimal control, of regulation to the origin on some desired state in the face of uncertainty, and so on. Now, under favorable assumptions, the results that are available here are almost as strong as for the discounted case. These favorable assumptions preclude the optimality of non-contractive policies. And the contractive policies here, in the context of shortest path problems, are the ones that terminate with probability 1 from every starting state. Non-terminating policies involve some kind of cycling through the graph without reaching the destination. These favorable conditions arise when the non-terminating policies can be ruled out from optimality, for example, when there is high or infinite cost for cycling. However, in the absence of such favorable assumptions, very complex behavior is possible, as we will see later in this lecture. In addition to shortest path problems, there are other types of non-contractive problems. For example, problems that involve a discount factor and the cost per stage is unbounded belong, mathematically speaking, to the non-contractive class, and they exhibit similar complex behavior as the shortest path problems. There is a class of undiscounted problems that has better structure and for which some favorable results are possible, and these involve either a uniformly negative cost per stage or a uniformly positive cost per stage. We're going to touch upon some of these problems later. In this lecture series, we're going to focus on semi-contractive problems. These are intermediate between contractive problems and non-contractive, and their characteristic is that some policies in these problems are well behaved and some are not. Now, the meaning of well behaved depends on the problem. The most common example of well behaved policy is one that is contractive, but there are also other examples. Generally speaking, well behaved is related somewhat loosely to a notion of stability. The well-behaved policies keep algorithms like value iteration stable and convergent, whereas the well-behaved policies, not well-behaved policies, do not, and can cause pathological behaviors. Our approach in dealing with these problems is to select a class of well-behaved policies, and mathematically we're going to define them more precisely later, and we're going to call them regular. Then we're going to define a restricted optimization problem over just the regular policies. We're going to show that the restricted problem has nice theoretical and algorithmic properties, and we're going to relate the restricted problem to the original. Finally, under reasonable conditions, we're going to carry over our results from well-behaved policies and restricted optimization to the original problem and obtain strong theoretical and algorithmic results. Let me give some references to this work. The starting point is a research monograph called Abstract Dynamic Programming, which I published in 2013. Since that time, some of the results were improved, and at this point you can find updates to the Semicontractive Chapter 3, which contains some of the new research. Now, this research, in greater detail, in fact, is contained in a series of papers. This paper here provides an extension of the notion of regular policies. It's a theoretical paper that also affects some of the material in Chapter 4 in this research monograph. The next paper deals with affine monotonic models where the dynamic programming mapping is linear, and these include risk-sensitive models with exponential cost function. Then this paper deals with minimax type of shortest path problems. Robust refers to minimax. The next paper deals with optimal control problems with continuous state space, which are the basis for the field of adaptive dynamic programming. Finally, a joint paper with my longtime collaborator, Hujin Jenny Yu, which has been around for some time, and the latest version is given in a report from January 2016. Let me now summarize the contents of this lecture series. In the first lecture, this one, we're going to deal primarily with examples as well as general orientation. In the next lecture, we're going to pass into mathematical analysis of semi-contractive problems, but for a special case, the familiar case of a stochastic optimal control problem. In the third lecture, we are going to discuss abstract dynamic programming problems. These are generalizations of the stochastic optimal control problem, where the Bellmans equation mapping takes a more abstract form, and these models apply to a broad variety of dynamic programming situations, like semi-Markov problems, like minimax control problems, risk-sensitive problems, and so on. Then we're going to discuss various applications. A standard example is going to be stochastic shortest path problems, but we are going to discuss also several other types of problems, some of which involve the notion of a shortest path, For example, robust shortest path planning, which is a minimax type of shortest path problem, and shortest path problems that involve a multiplicative cost function and or more specifically an exponential cost function that have a risk-sensitive structure. Finally, we're going to discuss algorithms of the classical varieties such as value iteration and policy iteration, but also more exotic versions, for example, versions that can be operated asynchronously or involve some kind of weaker conditions for convergence, and this is going to be done in the last lecture. Okay, we're still looking at stochastic optimal control problems characterized by a one-stage cost function G and a discrete time system equation involving the function f. We will use a shorthand notation to simplify expressions such as Bellmans equation. We will denote the expression that appears in the right-hand side of Bellmans equation by using a function h, which is a function of h, x, u, and j. And with this notation, Bellmans equation takes this form. Now, the first result that we hope to be true is that J star satisfies Bellmans equation. There is also another result, a sufficient condition for optimality, and usually necessary, which says that if mu stars of x is a control u that attains the minimum, the infimum in this expression, for every x, then the stationary policy mu star thus constructed is optimal. So this is a necessary and sufficient condition for optimality typically. Regarding algorithms, an important method is value iteration, which starts from some initial function j0 and generates a sequence of functions jk, which we hope and expect to converge to j star. So given j0, we obtain j1 by applying the Bellman equation mapping to j0, the dynamic programming mapping. Then we obtain from j1, we obtain j2, then j3, and so on, the whole sequence. Jk is the optimal cost associated with a k-stage problem with terminal cost j0. And what we hope to be true here is that the optimal finite horizon cost converge to the optimal infinite horizon cost. Another important method is policy iteration. Here, instead of iterating with functions, we iterate with policies. We start with a policy mu0, then generate mu1, then mu2, and so on. And we hope and expect that this sequence of policies will be asymptotically optimal. In other words, the corresponding sequence of cost functions converges to the optimal cost function. Moreover, we may hope that this sequence of policies will converge in some sense to a policy that's optimal, and this is indeed often true. Now, the way we go from mu k to mu k plus 1 is a two-part process at each iteration, at the kth iteration, whereby given the current policy mu k, we evaluate it. In other words, we find its cost function by solving the corresponding Bellmans equation. So after we have evaluated mu k and obtained this j mu k, we stick it into Bellmans equation and minimize, and we obtain a new policy mu k plus 1 by this minimization, which is done for every state x. This is called policy improvement, and the reason for this terminology is that usually, although not always, mu k plus 1 is a better policy than mu k in the sense that its cost function is uniformly no larger than the cost function of mu k. We will now consider some examples that are pathological in the sense that the results that you expect to hold, as in the preceding slides, do not hold. In particular, Bellmans equation may not hold, or value and policy iteration may not work as expected. In all of these examples, there will be a set of well-behaved or regular policies. For instance, in shortest path problems, the regular policies will be the ones that reach the termination state in finite time. There will also be some policies that are not well behaved, and let us continue to denote by j stars of x the optimal cost over all policies starting from x, and let us introduce some new notation. Let us consider optimization over just the regular policies and denote by j hat of x the optimal cost over the regular policies only starting from x. So j hat cannot be smaller than j star, but it could be strictly larger, at least for some states. As an overview of the four examples, in the first example, we have a finite state, finite control, deterministic shortest path problem. In fact, it involves just a single state plus the destination. It's the simplest problem that you can possibly encounter in dynamic programming and for which you have somewhat unusual behavior. In this example, Bellmans equation may have multiple solutions. In fact, an infinite number of solutions, including j star and j hat. And it is also possible that the value and policy iteration methods do not work. They may not converge to j star or to j hat. In fact, the policy iteration method may not have the policy improvement property. It may generate a sequence of policies that oscillate in terms of cost and include strictly suboptimal policies. Second example is again a finite state, finite control problem, a shortest path problem, but stochastic. Now, in this problem, j star does not satisfy Bellmans equation. J hat does, but j star does not. And the key fact here is that this problem is stochastic. For deterministic shortest path problems, Bellmans equation is always satisfied. Perhaps it may have many solutions, but these solutions include j star. However, for stochastic problems, this is not necessarily true, even though it turns out that j hat is a solution of Bellmans equation. The third example involves a finite number of states, in fact only one plus a destination, and an infinite number of controls. It's a stochastic shortest path problem. All policies turn out to be regular in this example. However, there is no optimal policy, and also value and policy iteration exhibit some peculiarities. This is a classical counterexample called the blackmailers dilemma. It has been used in the past to show and to demonstrate unusual behavior. It comes in several different versions, and depending on the data of the problem, you may have different kinds of peculiarities showing up. The fourth example is a simple instance of a classical optimal control problem, one that involves a linear system and a quadratic cost function. This is not a contractive problem because there's no discount factor, and also the cost function is not bounded. The cost per stage is not bounded. Here it turns out that Bellmans equation has exactly two solutions. One of them is j star, the other one is j hat. And it turns out, however, that value and policy iteration typically are attracted to j hat and not to j star. In this example also, there is no notion of termination, and the regular policies are not the ones that terminate, but instead they have a stability property. They stabilize the closed loop system. Okay, so let us now consider our first example. So this is a deterministic shortest path example involving this very simple graph. There's a single node, node 1, and also the destination. If you reach the destination, you terminate and stay there at cost 0. At node 1, you can choose one of two actions. One is U, which takes you directly to the destination at a cost B, and the other one involves a self-cycle. At node 1, if you choose U prime, you stay at 1 at no cost. So the distinctive feature of this example is that there is cost 0 for just idling, just staying in node 1 and postponing going to the destination. If the costs were strictly positive here at node 1, staying at node 1, then you would want to go to the destination as quickly as possible, because staying at 1 would cost you something positive, which would accumulate to infinity over a long time. On the other hand, if the cost is negative, then you would want to stay at node 1 forever, and that's not a very interesting problem. The more complicated problem is where the cost is 0, in which case there are two policies, two stationary policies. One is the policy mu that takes you directly to t associated with choosing u, and the cost associated with that is b, the cost starting at node 1. The cost of starting at node 1 with policy mu prime that chooses u prime is 0. So we know the cost of the two policies, and we also know the optimal cost is the minimum of the two. Now, the cost of state t, we know that it is 0 under all policies, so it makes sense in this situation and also in other similar situation involving the destination to just fix the cost at t of all functions involved in Bellmans equation or in optimality conditions or in various algorithms, to fix it at 0 and just forget about it. This simplifies expressions and facilitates the analysis, and we're going to do this here. So we're going to worry only about the cost at state 1, which is the only one that's important. So that cost satisfies Bellmans equation, which is written in this form. It's the minimum over the two possible actions, choosing control u, which costs b, and then the cost to go is 0, or choosing control u prime, where cost is 0 and the cost to go is j1 because you stay at j1. So this is Bellmans equation, and now we see that this equation has an infinite number of solutions. All the j1 that are less than b are solutions, as you can easily see from here. So the optimal cost is certainly a solution of Bellmans equation, but there's also a lot of other solutions. If you look at the two policies, policy mu is the one that terminates, and we can view this as a well-behaved or regular policy, but the policy mu prime that stays at state 1 is not well-behaved. So remembering our notation of j hat being the minimum overall well-behaved policies, we see that j hat is equal to b. And j star, of course, we have already calculated it, is equal to the minimum between b and 0. And we note that depending on whether b is positive or negative, we can have equality between these two, or j hat may be strictly larger than j star. Okay, so let us consider now value iteration starting from any initial condition, j0 so 1. Then it involves the application of the mapping, of dynamic programming mapping on the current jk, and it's given by this expression. Now, when you look at this equation, you can see some interesting behaviors. First, suppose that b is negative, so it's optimal to go directly to the destination. J star is equal to b. Then you can see that starting from above B, starting from above J star, decreases Jk all the way to the point where it reaches the value B, and then in which case we have convergence. In fact, finite termination. Jk's of 1 converges to J stars of 1. So value iteration for B negative works, at least starting from above B. Starting from below B, value iteration does not work. The reason is that all the values less than B are solutions of Bellmans equation, so value iteration starting at any one of these solutions, any J, 0, that's less than B, stays at J0 and does not converge to J star. This is true generally when you have Bellmans equation have multiple solutions, then starting from any one of these solutions, value iteration will not make any progress, will have no change. Okay, so now let's consider the case where B is greater than 0, so it is optimal to spin around this self-cycle. Then, if you start a value iteration from something above B, then you can verify from this algorithm that value iteration will converge to B hat, which is B, and not J star. If B is greater than 0, then we have a set of fixed points that extends from B all the way to minus infinity, and J star is somewhere in the middle of this interval here, and starting at any initial value less than B is going to keep you at that value. So the only way you can converge to J star is if you start at J star. Okay, so value iteration is for the problem is somewhat flaky. Let's consider value iteration restricted to the two policies. So value iteration for the regular policy considers only the transition to the destination, and it has this simple form, and it works. It gives you in one iteration, it gives you the cost of that policy, of the regular policy. So for the regular policy, we have value iteration working, and we're going to see that this is the critical property that regular policies should have. They should be well behaved with respect to value iteration. But that is something that we're going to encounter quite a bit later. Now, value iteration for the irregular policy mu prime that spins around along this self-cycle has this form here. The Bellman equation mapping is just J's of 1, and so starting at any initial value stays at that initial value, so value iteration apparently fails for this irregular policy. So altogether we have an infinity of fixed points, of infinity of solutions of Bellman's equation. Value iteration does somewhat strange things, particularly when it involves irregular policies. If you look at policy iteration, things are not much better. If B is less than 0, when it is optimal to go straight to T, something very strange happens. Policy iteration can oscillate between the optimal policy, which is mu, and the strictly suboptimal policy, which is mu prime. It can go up and down and never converge. If B is strictly positive, on the other hand, in which case the spinning around on the self-cycle is optimal, then policy iteration converges to the suboptimal policy. It does not find the optimal policy, finds something that's strictly suboptimal, but it is optimal within the class of well-behaved or regular policies. Our next example involves a stochastic shortest path problem. Here there is a single policy, and we will see that it does not satisfy Bellmans equation. In this example, there are 7 nodes plus the destination T, which is cost-free and absorbing, and there is uncertainty only at the first node, node 1. Here we can go with probability 1/2 along the left branch and with probability 1/2 along the right branch. The costs in the 2 cycles are deterministic, and they are selected so that the costs that are incurred on the left cycle are exactly the opposites of the costs that are incurred in the right cycle. So when we start at state 1, there's probability 1/2 that we are going to be incurring these costs, and probability 1/2 that we are going to be incurring these costs. And since these costs are opposites of each other, they cancel each other out. And the cost of the policy starting at state 1 is equal to 0. Now let's look at the cost of the policy starting at state 2. Upon entering state 2, we incur a cost of 1, then a cost of -2, which brings us to a sum of -1, then a cost of 1, which brings us to a sum of 0. So we start at 1, go down to -1, then to 0. Then again, as we spin around the cycle, 1, -1, 0, and so on. So the finite horizon costs starting at state 2 are oscillating, with an upper limit of the oscillation being equal to 1, and so the cost of the policy is this upper limit, and it's equal to 1. Now if we start at state 5, a similar thing happens, except that the costs are reverse of each other. We start at -1, go to +1, and then to 0. -1, +1, and then 0. And the upper limit is again equal to 1. So the cost of the policy starting at state 5 is equal to 1 here. Now, if you look at Bellmans equation, it is given by, it must be, J mu of 1 must be 1/2 the 2 costs at 2 and 5, but it is violated because the cost at state 1 is 0 and it's not equal to this. So here we have, even for a single policy, Bellmans equation violated. And this is a rare phenomenon, but it's still possible when costs are both positive and negative in stochastic shortest path problems. Let's mention also another somewhat peculiar phenomenon here. Suppose that instead of the stochastic shortest path problem, we consider a deterministic problem, where at state 1, instead of moving with probability 1/2 to the left or 1/2 to the right, we have a choice. We can either choose to go to the left or choose to go to the right with probability 1. So this is a deterministic shortest path problem. And clearly, no matter which branch we choose, we're going to have a cost equal to 1 starting at state 1. So Bellmans equation here is satisfied. But suppose now that we take this deterministic problem and we randomize, so that instead of so that we can choose a probability for going to the left or to the right. It turns out that the optimal probability is 1/2, and then the cost at 1 drops down to 0. So while Bellmans equation is satisfied for the deterministic problem with optimal cost equal to 1, by introducing randomization, we lower the optimal cost to 0, and at the same time, Bellmans equation is violated. Okay, our next example deals with the so-called blackmailers dilemma, which is a stochastic shortest path problem involving a single state 1 plus the termination state t. This problem models the behavior of a blackmailer who at each time period demands a certain amount u, that's between 0 and 1, it has to be positive, and the victim will refuse to pay with probability u squared, and will pay with probability, the complementary probability of 1 minus u squared, And this process goes on continuously until the victim refuses to pay, and we get to the termination state, but the blackmailer gets to keep all his rewards up to that time. So what we have here is an infinite number of policies, one for each stationary policies, one for each u. And now what's important to note here is that if a policy demands a small amount u, the corresponding probability of being denounced to the police is much smaller, and as a result it pays to ask for small amounts of money at each stage in the expectation that you will keep collecting for a large number of stages. If you calculate the cost associated with a stationary policy, you'll find that there is a probability 1 of eventually getting to the termination state. On the other hand, the associated cost is the negative of the total reward collected is 1 over the amount demanded. So if mu sub 1 is chosen very close to 0, then the corresponding cost of the policy is very negative and approaches minus infinity as mu sub 1 goes towards 0. So we have an optimal cost of minus infinity, but there is no policy that attains this cost. It can be approached from above, but it's not possible to actually attain the optimal cost of minus infinity. What's peculiar here is that all policies are well behaved. All policies terminate and have this regularity property that we have discussed, and yet we have this phenomenon that there is no optimal policy. Moreover, if you write Bellmans equation, it takes this form. This equation has no solution in the set of real numbers. It is satisfied by the optimal cost, which is minus infinity, but it's not satisfied by anything else that is any other number that's real. Value iteration turns out to be reasonably well behaved in the sense that starting from any scalar j and applying this dynamic programming mapping repeatedly, we get a sequence that converges to the optimal cost j star. Policy iteration also has somewhat reasonable properties. It generates a sequence of policies, all of which are regular, well-behaved, they terminate, and the corresponding sequence of policy costs converges to the optimal cost. On the other hand, the policies themselves converge to 0, which is not an admissible policy. So we have convergence in the space of costs, but not in the space of policies. This problem has several variations. One possibility is to replace u squared with u. Then the optimal cost turns out to be finite. It's minus 1. However, there is no optimal policy again. If you look at Bellmans equation for this problem, you'll find that it has an infinite number of solutions. All scalars less than minus 1 are also solutions, including the optimal cost. So we have an infinity of solutions of Bellmans equation. There are also some other variations of this problem that have interesting behavior, and you can look them up in the readings. It's sort of an interesting example, but for the moment we leave it at that. Our next example is a linear quadratic problem involving a linear system and a quadratic cost function per stage. The state is xk takes values in the real line. So the state space is a real line. The control space is also the real line. There are no constraints on control. And the next state is obtained according to this linear equation where gamma is a fixed scalar. Now, because there is no penalty on the state, only on the control, it is always optimal to apply zero control, incur no cost. So the optimal cost function is identically zero, and the optimal policy is identically zero also. Bellmans equation takes this form. It involves the sum of the first stage cost plus the cost to go starting from the next state. And it is satisfied by J star. One may also ask here whether there are any other solutions of Bellmans equation. It turns out actually that this is an interesting question that has been investigated in the literature of linear quadratic problems, which is quite voluminous since linear quadratic problems is one of the most important classes of control problems, perhaps the most important, and it has been investigated extensively. Now let's look at this question of solutions of Bellmans equation, and let's assume that gamma, the coefficient of xk in the system equation, is strictly greater than 1. So the system is unstable if left uncontrolled. Now, if you apply the optimal policy to this unstable system, it will stay unstable, so the closed loop system is going to be unstable, and even though this policy mu star is optimal, it is not very satisfactory from a practical point of view. Now, looking back again to Bellmans equation, it turns out that it has a second solution, which we are going to denote by j hat, and it is given by this quadratic expression. Through analysis, it is possible to verify that this j hat has an interesting interpretation. It is the optimal cost function of a restricted problem, where the policies are restricted to stabilize the system. Well, these stabilizing policies may be viewed as well-behaved or regular policies, and j hat is the optimal cost over the well-behaved policies. It's the j hat that we mentioned earlier in this lecture. So j hat is not the same as j star. It solves a Bellmans equation, and it turns out that Bellmans equation has just these two solutions, j star and j hat. Now, if you apply the algorithms of value iteration and policy iteration, they tend to be attracted to j hat, not to j star. In particular, policy iteration started with a regular policy, a stabilizing policy, generates a sequence of stabilizing policies that converge, that have costs that converge to j hat, the optimal cost of the regular policies. Value iteration, if started with any function that's positive rather than 0, converges again to j hat, not to j star. Of course, its value iteration is started at j star, it remains at j star and converges, but that's not very interesting. In the general case, we don't know what j star is. It can be shown that this kind of behavior is generic in linear quadratic problems that have this instability property, and also involve a somewhat peculiar structure of cost per stage where the state is not fully penalized. And actually, this behavior of the optimal controller in linear quadratic problems has been investigated early on, since the early 70s, and has received some attention. It is interesting that phenomena that were investigated so long ago in this class of problems can also be interpreted in terms of well-behaved policies and semi-contractive dynamic programming, as we are going to discuss in the coming lectures. Let us now summarize the behavior that we have observed in the preceding examples. One thing that we saw is that Bellmans equation may have multiple solutions. It may have one solution, an infinite number of solutions, or a finite number of solutions, as we saw in the preceding linear quadratic example. We saw in one example that J star, the optimal cost function, need not solve Bellmans equation. Often, and J star is a solution, but it's not always true. We saw a restricted optimization problem involving optimization over the well-behaved policies, and we saw that such a problem is often meaningful and plays an important role in the analysis. For example, its optimal cost function, J hat, is a solution of Bellmans equation typically. The choice of well-behaved policies in a given situation depends on the problem. However, with some experience, one can guess on an appropriate set of well-behaved policies. For example, terminating policies in shortest path problems have a contraction property, which makes them suitable. In the linear quadratic case, the stabilizing linear stabilizing policies are also appropriate. Generally speaking, we will see that well-behaved policies are the ones that behave well with respect to value iteration. Their cost function can be obtained by value iteration using the corresponding Bellman equation mapping. The J hat, the optimal cost over the well-behaved policies, may be different than J star. And it turns out that in some of these examples, we saw that J hat is the likely limit of the value iteration and policy iteration algorithms, and not J star. There's also the complicated issue of figuring out the set of initial conditions from which value iteration and policy iteration work. Now, in our next lecture, we will aim to explain this behavior through analysis, formalize the notion of well-behaved policy through a notion of regularity, and introduce the kind of assumptions under which anomalous behaviors such as the ones that we have observed can either be avoided or mitigated. And once we introduce assumptions of this kind, we will be able to obtain results that are nearly as powerful as the ones for contractive problems. Okay, we have concluded this first lecture in this lecture series, which dealt with an introduction to the subject of semicontractive dynamic programming and an illustration of behaviors that we can expect and we would like to address through examples. In the next lecture, we're going to do a mathematical analysis of the type of phenomena that we have observed, and we are going to restrict ourselves to stochastic optimal control problems. Then we are going to extend the analysis of the second lecture to abstract DP models, we are going, in the fourth lecture, we're going to discuss various applications such as stochastic shortest path problems, affine monotonic problems, minimax type of shortest path problems, and optimal control problems of the type that we saw in the linear quadratic context. Finally, the last lecture will deal with computational algorithms, value iteration, policy iteration, and variations of those that are tailored to addressing the difficulties that we have discussed.